Okay. What more could you possibly want to know about second order? We've looked at 4 different varieties of second order circuits. We've had source-free, series, and parallel, and then step response for series and parallel. We found there's a homogeneous and a steady state. Homogeneous is also called the transient response, and we look at the ways of solving those. The form of the solution is some final value plus the sum of 2 exponentials, and we dig into the circuit to find the initial conditions that will allow us to determine what those coefficients are. And there's a sort of a difference between series and parallel in the definition of alpha. For parallel circuits, alpha equals 1 over 2 RC. For series, it equals R over 2L. So you have to kind of make sure you're using the right formula for alpha. And then, you know, once you find I for a parallel or V for a series step response, you can find other circuit variables using differentiation or Kirchhoff's current law or KVL. So that's what it's like working with second order circuits. And then we looked at the idea of a general second order circuit. We went through all this yesterday. And now we're going to actually apply that. So we have a circuit that's a second order circuit, which is neither series nor parallel. So that whole process we've been showing you, which is sort of developing the ODE that describes you know, finding the solution, solving the conditions, and setting up all those things. We're just going to apply this now in an unfamiliar circuit. So you can take this skill set and apply it to any second order circuit that you might need to solve. And believe me, there are tons of them out there. I don't know how you'll be using it, but it's a skill we're going to sort of master here. So the trick is, well, we have a second order circuit. It has an L and a C, so it's a second order circuit. If it had 2 capacitors that were not easy to combine, then it would also be a second order circuit. Like if there was a capacitor here too, this could also be considered. If this is a capacitor, you couldn't combine it with the other capacitor. So it could also be a second order circuit. It doesn't have to have an L and a C. It could be 2 C's or 2 L's. Just 2 energy storage components. And the circuit has a switch that's initially open, and then it closes at t equals 0. And we can focus on the transient response, and then that's what this thing is here. We're going to first solve the transient response, and then we can add to it the steady state response. Just to find to kind of put that all together. So the transient response is where we take out the source, and that's where you're going to have all that the sum of the exponentials. The sum of the exponentials is really what the transient response is all about. And the nice thing for that part of the solution, we can just throw out the source. And we turn off the source, so that source is turned off. And we have to find a solution for the circuit variables in terms of one variable that we can then we're asked to find V of t and I of t for t greater than 0. So V of t is the voltage across the capacitor, and I of t is the voltage through the inductor. So they're still labeled on there. Okay, so let's see. If we look at this circuit, we can tell that well, we have this sort of node here, and actually conveniently the voltage V has been put up there. We would also have a a ground here. That's a node voltage. So we can sort of figure out the current IC from the voltage of the capacitor. We can figure out the current going through the 2 ohm resistor. That's just going to be V over 2. And we could figure out the voltage across the inductor as VL if we wanted to. And we could start with what would be a good equation to kind of start this analysis with. Any ideas? Audience participation? We got a few of these things here. We got the I going through the inductor. We got the V of the capacitor. We got IC. What's a good starting point? What do you think? What would you do if you were sitting there looking at this circuit? You had to go to the next step. Isaac? Do mesh analysis? You could. You could do mesh analysis. You could also do nodal. You could do KCL. You got a node voltage right there. I think KCL is going to be a little simpler, so let's just try that. If you were going to try mesh analysis, you would maybe have an I here. You'd have to come up with a name for this mesh current here. I guess this mesh current would be IC, wouldn't it? Yeah, you have an I and an IC, so you could do mesh analysis. Yeah. My notes say KCL. Doing KCL at A says, what do you got? Well, you got I going into that node voltage. This is the node A here, or A, voltage of V. You got minus V over 2 leaving it. And you got minus IC leaving it. That has to equal 0. And you've got this IC, which is C dV dt. Allows us to write something like this, that, I minus V over 2 minus 1/2 dV dt equals 0. So that's a start. Still have 2 unknowns in there. But this I has a little more going on with it, right? Because that I is coming through an inductor. The inductor has a VL in it, and a resistor that's also involved. So I think we have to capture that as well. So so we will do a kind of a mesh analysis, which is a KVL equation. Kind of doing both here. KVL here in that left mesh here says you've got say 4I plus VL plus V equals 0. So 4I plus VL, which is L di dt, so that's going to be 1 times di dt, plus V equals 0. But we could separate out the I and solve for that from equation 1. So from equation 1, this is our second equation here. Let's just circle that or box that up. But from equation 1, we know that I equals, we could solve for I equals V over 2 plus 1/2 dV dt. And so we could plug this into here. We could also differentiate that, though, before we do that. And if we differentiate that, we'll find that di dt equals 1/2 dV dt plus 1/2 d squared v dt squared. So that gives us both a value for I and di dt that we can plug into there. You're going to get this kind of nasty equation, but basically, you know, 4 times the sum of, well, the I, which is v over 2, plus 1/2 dv dt, plus di dt, which is going to be 1/2 dv dt plus 1/2. D squared v dt squared, and plus v equals 0, combining those two equations. So you're kind of messing with this stuff until you can get a single differential equation in terms of one variable. So we're going to eventually combine everything together. We're going to have 1/2 d squared v dt squared plus 5/2 dv dt plus 3 v equals 0. And then multiplying everything by 2, we're going to get finally d squared v dt squared plus 5 dv dt plus 6 equals 0. So that is our governing equation. And 6v, sorry. 6v equals 0. And that gives us the characteristic equation that s squared plus 5s plus 6 equals 0. And that one you can actually factor into s plus 3 times s plus 2. So s is going to equal minus 3 s1, and s2 is going to equal minus 2. You already know it's overdamped. And again, this is just the transient response. So we know the transient response then is going to have the form of a1 e to the minus 3t plus a2 e to the minus 2t. Wait for there to be a loud noise. Come on, I can't eat. You can't eat in front of me. So the transient is going to be of a1 e to the minus 3t plus a2 e to the minus 2. I'm just kidding. So someone in the materials engineering class should invent a material that allows you to open food packages without making a loud noise. Low noise plastic wrappings. But that's just the part of the solution. We also have to consider the steady state, which is the infinity, the final value of V in this circuit. And the final value of V is going to be looking at that circuit long after everything is stabilized. When the I hope I don't need to tell you that the inductor becomes a short circuit and the capacitor becomes an open circuit. And this is V infinity. And it is a voltage divider formula problem. So V infinity by inspection is going to equal 2 over 6, 1/3 of 12 is going to equal 4 volts. Right, you can see the voltage divider in there. You've got the 4 and the 2 ohm. When the inductor becomes a short, the 4 and the 2 becomes a series combination, and the capacitor voltage is really tied to the 2 ohm resistor. Basically. Yeah. Mm-hmm. So when I'm done with this line. So V infinity is 4 volts. So the solution, total solution, is going to then be V infinity plus V transient. And when we assemble everything together, we can then solve for the boundary value, those coefficients. So the V of t is going to be 4 plus a1 e to the minus 3t plus a2 e to the minus 2t. Infinity? VDE, voltage divider equation. So that our, our initial conditions are that IL of 0 minus from the no jump rule, and well, what is IL of 0 minus from the no jump rule? Before the, what does the circuit look like before? So with an open circuit there at the switch there, what was IL of 0 minus? Before that switch closed, what was the current? What was IL of 0 minus? Yeah, why? Yeah, the IL 0 minus is 0 because with this switch open, you have basically a single path. It's a single loop circuit, and you have a capacitor, which in the steady state is an open circuit, so all the current going into it is 0. So IL of 0 minus is 0. Isaac? Steady state, is that when the switch is open or closed? Steady state is when things have been the same way for a long time. It doesn't matter what the position of the switch is. So they typically tell you the switch has been open for a long time before it closes at t equals 0. That's telling you it was in the steady state before the switch closed, which is how we're going to find our initial conditions. And then there's the final value, which is when it's once again in the steady state. So it's moving from steady state to steady state. And what is VC of 0 minus? $12. Yeah. Basically have an open circuit attached to a 12-volt source, right? That's 12 volts. So so we need V of 0, and that's going to be 12. But we also need dV dt at t equals 0. But we know that dV dt at t equals 0 is what? We've done this over and over again, right? IC of 0, and then what? Over C, right? Yeah, IC of 0 over C. So we just have to find what IC of 0 plus is, right? And this is the tricky thing. This is a tricky thing. So in this case, we'll redraw the circuit. where the inductor and the capacitor are at their initial values from C equals 0 minus. Basically.
On the previous slide, we were in the equation with IL, basically the KCL.
Uh-huh.
Can we plug 0? Can I plug 0? Can we find dVt at 0 for finding I of 0 and d over 2 of 0?
Maybe. Why don't you try doing it that way? So Mason's question is, if we have this equation right here, can we use this equation to solve for IC of 0? Or basically, you want to solve for to solve for dVdt of 0. Since you know what V is and you know what I is. I is 0 and V is 12. Well, it's trivial, right? So what you're saying is, according to that rule. Now, I'm not so sure because this doesn't take into account the fact that, well, what does it do? Yeah, so let's see what happens. So if this is true, then dVdt should be 2 times I minus V, right? Do you agree? Just doing some algebra in your head. If we could use this, this is telling us that if we're solving this for dVdt, and this is sort of an experiment here, dVdt should equal 2 times I minus V, right? So I is 0 and V is minus 12, right? So according to this, dVdt should equal minus 12. Does it equal minus 12? That is the question. And the answer is yes, it does. But the other way to do it is using KCL, KVL, and the circuit. This is a way that I don't know. It seems maybe, I don't know if you like that better, but it's nice to know that you can do it either way. But a typical approach is to draw the circuit. At t equals 0 plus. At t equals 0 plus, IL of 0 plus is 0, because it has to be the same as it was at 0 minus. And I is going to be, well, and VC of 0 plus equals 12 volts. And so I, through the resistor, is going to be 6 amps, because you got 12 volts over 2 ohms. And we need to find IC of 0 plus. And IC of 0 plus is going to equal minus 6 amps, because the inductor is not going to be accepting any current, and the resistor is going to have 6 amps going through it because the capacitor is at 12 volts. So the capacitor has to be dumping out current. The capacitor has to be dumping out the current that's providing the resistor 6 amps. Right? And so if the capacitor is dumping out current, it's going to be dropping voltage, right? And the rate of that drop is going to be IC over C. So dVdt at t equals 0 is minus 6 over C, which is a half, so that's going to be minus 12 volts per second. Isaac. Steady state would be what? And then 0 minus. No, the steady state, when steady state is actually happening, the two times when steady state is actually present is at 0 minus and at infinity. 0 plus is after the disturbance. You know, you're disturbing that circuit when you throw that switch, and that creates a disturbance. However, the way we can determine the boundary conditions is that the inductor current is going to not jump from that disturbance. It can't jump from that disturbance. The capacitor voltage cannot jump from that disturbance, but everything else can jump. So that's the transient. The transient response is kind of governing from 0 plus to less than infinity, sometime less than infinity, a lot less than infinity, right? Because at infinity, the transient goes to 0 completely. Okay, so now we have everything for our boundary conditions. We know that B of t equals 4 plus a1 e to the minus 3t plus a2 e to the minus 2t. We know that v of 0 is going to equal 4 plus a1 plus a2, and it has to equal 12. And we also know that dv dt in general is going to equal minus 3a1 e to the minus 3t minus 2 a2 e to the minus 2t. And dv dt at t equals 0 then must equal minus 3a1 minus 2a2. And it must equal minus 12. And we can solve those. Or you could solve them. Anyway, they're solvable, right? So do we want to solve them? Want to see what the solution looks like? I don't have the solution here. So basically, k1 plus k2 x plus 1 and minus 3x minus 2y equals minus 12. It says a1 equals minus 4 and a2 equals 12. That sound right? Why did my screen disappear? Huh. There we go. A1 equals minus 4, A2 equals minus 12. Does that work? Wait, what? No, plus 12, sorry. A2 equals plus 12 because minus 3 times minus 4 is plus 12, minus 2 times plus 12 is plus 20, is minus 24. Yeah, 12 minus 24 is minus 12. Yeah, that works. So that's the whole solution. So so V of t is going to equal 4 plus, I guess 4 minus 4, 8. and then plus 12 e to the minus 2t. Yep, so the initial value, you plug in 0 there, the initial value is 12, and the final value is 4. It goes from 12 to 4 volts. With an initial slope of minus 12 volts per second. So, I mean, if you were going to sketch this thing, you don't really have to, weird. Thought I had a slide right there. I mean, but essentially it's going from 12 to 4, and it starts off with a, and it's not really oscillating like it looks like it's oscillating there. It should just be going basically like that, where the slope is at the 0 point is minus 12 volts per second. And it just tapers off at 4. Something like that. And we're asked to find, I think we're asked to find I too, right? Are we asked to find I? But now that we know what V of t is, we can solve for I using those other formulas. V over 2 plus a half dV dt will give us I. So that shows you how you can solve basically any second order circuit just working through that process. And then we have one more example here, which is, again, this is a source-free response. We would have to be given Vc of 0 equals some Vo, and IL of 0 equals some IO. Maybe we would be asked to find V of t. Again, this is neither a series nor a parallel circuit. But if you have a voltage here of V, then the circuit current through the form is going to be V over 4. You're going to have an IC. It's a similar type of process. You're going to have an IL going away. And this IL is going to also be going through the inductor, which is going to have a VL. Like so. And once again, it's just sort of noodling through the typical equations, just having differentials in them. So KCL is going to be minus IC minus V over 4 minus IL has to be telling us that IL is going to equal minus 1/2 dV dt, because that's what IC is, minus 1/4 V. So it looks like you try to solve for one of the variables in terms of the other. Try to solve for the inductor current in terms of the capacitor voltage, or try to solve for the capacitor voltage in terms of the inductor current. So you can do a substitution in the other equation. KVL is going to tell us that if we have IL circulating, well, you're going to have a minus V going in the outer loop. I got minus V plus 2IL plus VL equals 0. And just in case you didn't get that, the IC above was C dV dt. Just like the VL here is L di dt. DIL dt, which is dVc dt. So that's going to give us, whoops. That's going to give us minus V plus 2IL plus 1 DIL dt equals 0. Into which we can plug in the this equation here. We can also differentiate it and plug it in there. Or, right, we could solve for V and plug that into the other equation above, right? You could take that solution for V, for the second equation, and plug that into the equation above for I, and then you're going to solve for I. You know, so either one is appropriate. Either one will give you the same answer. And so putting all that together, again, you're going to get minus V, minus, and then you're going to plug in the 2IL. So that's going to be since it's a minus 1/2 dV dt, it's going to be minus dV dt minus 1/2 V plus minus 1/2 d squared V dt squared minus 1/4 dV dt equals 0. And you can multiply that whole thing by -4. So you're going to end up with 2 d squared V dt squared plus 5 dV dt plus 6V equals 0. And on and on and on, right? We could solve this one as well if you want, but I think you get the idea. I think just to get whole numbers. Yeah, no fractions, but it doesn't matter. I mean, yeah, you could multiply by -2 as well. Yep, so this is going to give you the characteristic equation, 2s squared plus 5s plus 6 equals 0. So your roots are going to be -5 plus or minus the square root of 5 squared plus 4 times 2 times 6. Oops, -4, sorry, not +4. All over 2 times 2. So that's going to give you minus 1.25 plus or minus 1/4 times the square root of -23. Or minus 1.25 plus or minus j times root 23 over 4. Well, I might as well just knock this thing out. So V of t is going to equal e to the minus 1.25t times a1 cosine of root 23t over 4 plus a2 sine of root 23t over 4. And in this case, we're given that you know, v of 0 equals v0. A1 and A2 are going to come from these initial conditions. V of 0 equals v0. I of 0 equals I0. And we're going to have to find, we're going to have to find dV dt at t equals 0. Equals IC over 0. Well, we have 9 minutes. Why don't you try doing that? That's such a good, challenging thing. Why don't you just try doing that right now? IC of 0 over C. dV dt at t equals 0, which is IC of 0 over C. Try to reason your way through that and see if we can come to an agreement. You're going to want to redraw the circuit where the initial values are applied to the capacitor and the inductor. It'll be in terms of V0 and I0. You're not going to have a number, but see if you can solve that. So you're going to redraw the circuit. So so find dV dt, t0 by first, redraw circuit at t equals 0 plus, and then set VC equal to V0, IL equal to I0, and then solve for IC. It's really 0 plus, not just 0. In case there's any confusion there. You got to be on the other side of that event. Yeah. Okay, so try doing that and see what you get for an answer. Isaac? There is no switch on this one. You're not understanding how there could be a 0 minus and a 0 plus. Yeah, well, yeah, you don't really need to worry about 0 minus and 0 plus per se. It's just that since you're given V0 and I0, that we usually use the 0 minus to find out what V0 and I0 are. And now they've just, somehow the circuit has been put in that state where it is V0 and I0 at t equals 0, and then something happens to let it go. But the instant after it starts moving, things are still at V0 and I0. So 0 plus sort of still applies. How do you know 0 plus? Yeah. It's the instant, it's really 0, but it, how do you find that on the circuit? It's just the same circuit. Just draw the circuit, and where the capacitor is, put V0, where the inductor is, put I0. And then solve for IC. Yeah. They're given to us in the problem. So it's given V0 and I0, solve for V of t. No, they're not. There's no numbers, but here, up on the upper right hand, I'm going to circle right now. Look up here. See right here? We're given this and this. These have to be given to us. So with those initial values, like I said, you're not going to get a number. Just do it in terms of V0 and I0. We're going to solve for IC. V0, this is an ion. Think about what's the current going through the resistor. This one?
Right? It's not exactly what we did.
Yeah. Same as what we got. Yeah.
Oh.
Yeah. Yeah, 2 minutes remaining. So yeah, you draw the circuit, and again, you can draw it as a capacitor and inductor, or you could put a source there, right? If you want to. This is the circuit where it's kind of helpful sometimes to draw the capacitor and the inductor as sources. But however you do it, there is going to be a V0 applied here, and an I0 going this way. And this is going to be our IC. And this is going to be, because you have a 4 ohm resistor, that is going to be V0 over 4. So you can do KCL. Which is going to say that currents leaving, currents entering are positive, so minus IC is 0, minus V0 over 4, minus I0, right, these are all leaving that node, equals 0. So IC of 0 equals minus V0 over 4 minus I0, and dV dt at t equals 0 is going to equal that divided by 1/2. So it's going to equal IC of 0 over 1/2. So that's going to give us minus V0 over 2 minus 2I0. So that becomes the boundary condition for, second boundary condition for finding A1 and A2. Okay. Well, I hope you enjoyed this little interlude on second order circuits. We're going to practice this tomorrow, so I really recommend that you be here for that. It's going to be on the test. Yeah. Speaking of test, I can't make it here tomorrow. But maybe I'll just not do it. Go. It's next Wednesday. Yeah. What does it say online? Is this on Friday? Well, it's going to be on Wednesday. Yeah. Yep. What's due for materials lab on Friday is those extra questions about your interpretation of the plots, what they mean. Yeah, that was awesome. Too bad. Yeah, you should have. I was wondering why you weren't there. I was like, yeah. goes. I was supposed to, I don't know if you're here Tuesday, but I mentioned, I forgot to mention in class anyway. Yeah, I was kind of thinking,